Today is all about the vertical component of traversing or using a total station to transfer the elevation from one point to another. We're going to cover how it's done, the errors associated with it, and I'm going to outline a novel technique to increase the vertical accuracy of your traverse to a point where it begins to rival what is capable using a differential level. A few weeks ago, I was sleuthing through LinkedIn when I came across a discussion on the merits of trigonometric leveling. In that conversation, a professional surveyor by the name of Jesse Kozlowski linked a paper he had written almost 30 years prior outlining a method of trig leveling that eliminates the largest source of error we surveyors encounter when transferring elevations using a total station, the manual measure-ups to the height of instrument and height of target. As I read through Jesse's paper, I couldn't stop myself from trying to figure out a way to take the theory behind the method he was outlining and use it to increase the vertical accuracy of a traverse. You see, Jesse's method is for one-dimensional surveys, when all you're after is elevations. I wanted to tweak it to borrow the benefit of mathematically eliminating your measure-ups, but while still performing a traverse, which allows us to define horizontal coordinates at the same time. So I poured a cup of coffee, popped in a Zen, and got to work. After messing around with some old data in StarNet, I started to realize I was onto something. That was a few weeks ago, and since then, I've field tested this new method I'm proposing, and the initial results are very promising. I believe I'm now at a point where I can share this method with the surveying community to offer an alternative to those situations where you need highly accurate coordinates in all three dimensions that have in the past typically been performed by 2D traversing followed up with a differential level run. This method is significantly faster and carries several other benefits as well. Let's get after it. Before we get into the fun stuff, let's get back to the basics. The theory behind using trigonometry combined with angles and distance measurements to transfer elevations from one point to another is actually fairly simple. Suppose we have a benchmark, let's call it point 1. If we were to set up our total station on another point, let's call it 2, and backsite that benchmark, we could define the elevation of the trunnion axis of our total station by taking the elevation of our benchmark, adding on the measured height of target, then adding the result of the cosine of our measured zenith angle multiplied by the measured slope distance. We could then get the elevation of the point our instrument is set up over by projecting the measured height of instrument down and determine the elevation of our foresight by using that same equation for height difference and subtracting our new height of target. Then we move our total station to the foresighted point, and this time, since we're set up on a point with a measured elevation, we can use our HI to get the elevation of our trunnion axis and continue on bumping the elevation from point to point in this manner. Now that we understand the fundamentals, let's start diving a bit deeper and looking into the error sources affecting that relatively simple equation. Without understanding each and every error source that affects our measurements, it's pretty difficult to make a conscious effort to reduce them. I like to lump these sources of error into 4 groups. We have the hardware group, or instrumental errors. We have the setup group, or operational errors. We have the atmosphere group, or the environmental errors. And last but not least, the Earth model group, or geodetic errors. First up in the hardware group, we have the compensator error. When we level our total station, the internal compensator is measuring gravity and aligning itself with a local gravity vector. And since any and every single measurement that ever has been made or ever will be made has error, we must consider the error introduced from the compensator measuring gravity because that measured plumb line makes up one side of the zenith angle we use to measure a height difference. Most spec sheets will quote an accuracy value for this. Then there's the other side of the angle we just talked about, the angular precision of a dual face pointing of your total station. When you hear someone say a 1 second or 3 second total station, this is the error source that the accuracy spec refers to. Next, we have the vertical collimation, otherwise known as the index error. This is a systematic offset where the zero of the vertical circle doesn't perfectly match the true zenith. The good news with this error source is that it's eliminated by averaging direct and reverse or dual face measurements. It can also be mathematically removed via instrument calibration. And let's not forget about our aiming errors. In this day and age, robotic total stations reduce this error via automatic target recognition, which has been proven time and again by peer-reviewed studies to be more precise than manual pointing. That being said, ATR isn't perfect. Testing has shown there to be a sweet spot in the ATR's capabilities in regards to distance from prisms. So if you push your observations out too far, your ATR accuracy goes down, and surprisingly fast, I may add. And if your ATR is out of calibration, you will be introducing systematic error in the vertical component. When doing any high accuracy vertical work with your total station, it's very important to have a freshly calibrated automatic target recognition system. I have a long-form video on my channel about automatic target recognition for those interested in this subject. And wrapping up error sources affecting the total station, we have EDM measurement error. Again, this can be found in your instrument spec sheet as both a fixed component along with a scalar value that grows with observation length and is denoted as ppm or parts per million. While these have a minimal impact on the elevation determination and the majority of their influence lies in horizontal positioning, I thought it was still worth mentioning. A seldom thought about but significant error source affecting vertical accuracy of traversing is the thermal expansion of target poles. Let's say we have a target pole of 1.5 meters that was calibrated to that length at 20 degrees Celsius or room temperature. If we're out surveying in -10-degree weather or a temp swing of 30 degrees, our target pole will actually have shrunk by over 1 millimeters. And probably more important is a worn out prism pole tip that shrinks the height of your pole compared to what it once was. Every couple of weeks or when I get a new pole, I'll use my total station to measure the height of my pole by taking a number of measurements on a fixed height mini tripod on a point whose height I measured using digital calipers, and then take a series of measurements on the pole I'm trying to calibrate on that same point and compare the elevations. The next group up to bat is the setup group or operational errors. This is where the human element comes into play and typically where the biggest accuracy killers reside. The most notorious error and the star of today's show is those height of instrument and height of target measure-ups. There are methods to reduce these errors. For example, I recommend you checking your tape measure for systematic error. I use digital calipers to make sure that the start of my tape is set correctly. I measure to the bottom notch of my S7 and Trimble Access automatically converts my slant height to a vertical one. If your instrument doesn't do this, you'll want to compensate for your slant measurement on your own. I use millimeters to measure height even when working in the United States, as it allows for more precision compared to guessing half hundredths of a foot. And height of target measurement can be greatly reduced using a fixed height pole. Trying to measure the HT of a prism on a tribrac can be tricky to do very accurately. We also have the vertical settlement of our instrument affecting our measured height differences. Typically, this won't introduce significant error, but it may, depending on your setup. Group 3 is all about how the atmosphere affects our measurements. As light passes through temperature and density gradients, it literally bends towards the Earth. This error is proportional to the square of your distance, which is why keeping your sightlines under a couple of 100 meters or so can be advantageous when high accuracy is desired and you're working in highly refractive conditions. Most field software and post-processing software compensate for curvature and refraction together via the C plus R correction, but refraction isn't constant. Warm layers of air near the ground distort light more. An easy way to picture how refraction bends light is when you stick your arm into a pool and it looks like it's bending. Now the same thing is happening, but to a lesser extent when we sight our prism. Where we see the prism isn't actually the true location of the prism because the light is being bent as it travels through temperature gradients in the atmosphere. To mitigate this, don't use mini tripods on a hot day when the sun is cooking the asphalt. Cloudy days with stable temperature or working at night has advantages. The fourth and final group are geodetic errors. Now there is so much to unpack here. We have the deflection of the vertical or the deviation between the plumb line measured at our instrument and the normal line to the ellipsoid at that location. We have the curvature correction, which I just talked about, but essentially the equation we used to calculate height difference assumes a flat Earth. So we must mathematically compensate for that, ideally using the specific radius at the instrument's location, but often an average value is used as well. And we have converging equipotential surfaces. Level surfaces are not parallel. They converge towards the poles because the Earth's gravity increases with latitude. Without an orthometric correction, even a perfectly measured loop will fail to close to zero mathematically. The secret to moving your traverse into the first order category isn't just by buying a more expensive machine, it's by using field and office methodology that either eliminates or minimizes as many of these error sources as possible. And no better place to start than that error source that is often the one to blame when our closing traverse shot isn't what we had hoped we were going to get. Those HI and HT measure-ups. We briefly talked about how to reduce HI and HT error, but we can take that a step further with some altered field methodology and advanced processing techniques. Like we saw in a traditional traverse, for every single setup, any error in our HI gets added on top of all the other vertical error sources. Likewise, HT measure-up error also gets dumped onto all of the other vertical error sources that affect its measurement. And since our traverse is building on top of each elevation set from the previous hub, that error tends to compound on itself as we make our way along. What if we could leave a kind of temporary benchmark without measuring the height of target in between each backsight and foresight, and use that to temporarily hold and piggyback the traverse elevation down the run? A measured prism that we define the elevation of when sighting forwards, then grab that elevation when sighting back to define the height of the trunnion axis of your current setup, which you can then project to the next temporary benchmark. Well, that's essentially exactly what I'm proposing we do. Going back to the example we started off with at the beginning of the video, this method starts off in very much the same way. But before we foresight our next traverse hub, we'll measure a point approximately halfway between our setup point and the next traverse hub. We have no requirement to ever set up on this point, and therefore we have a lot of freedom as to the kind of target used for this so-called common point. If I'm traversing in an area with structure around, I like to use ball prisms that can be very quickly set on wooden or ferrous surfaces by using a screw-in steel adapter or the magnetic nest it comes with. If I'm out in the open, I can quickly set a temporary point and use a fixed height rod or tripod and tribrac. I'll measure rounds to my backsight, common point, and foresight. Then when I move to my foresight, I'll measure rounds to my backsight, the common point I already measured, my next foresight, and another common point to brace this next leg. Other than that, the field procedure for common point traversing is identical to a normal traverse. And these so-called common points don't need to be physically in between each leg. Let's say you're traversing around a building. If you can set a point up above obstructions and see it from multiple setups, that's fine too. The key to this method is that there is a common measurement to a point whose height doesn't change from either end of whatever traverse leg you wish to fine-tune in post-processing. What this essentially allows you to do is use these common points to hold the elevation that will be bumped along the traverse instead of relying on the elevations of each traverse hub to push the elevation down the line. The elevation of each traverse hub that's set up on will still be defined by your height of instrument measure up, but any error in those measurements will only affect that specific traverse hub and won't compound into the network. Now that we have our traverse with common point ties between each leg, to remove the influence of the HTs and the HIs from the network elevation, we bring the raw observation data into a least squares adjustment program and remove all weighting from the zenith angles between traverse hubs. I use StarNet for this, but the process should be the same regardless of what least squares adjustment software you use, provided it gives you the capability to remove weighting from individual components of each observation. I don't want to remove the entire observation between traverse hubs, just the vertical component. To do this in StarNet, you use the fixity symbols ampersand, ampersand, star, inline the measurements between traverse hubs, which are my 100 series points in this example. The 200 series are my common points, and the 2000 series are just side shots to some ground control points I'm using for some aerial LiDAR testing. This tells StarNet to ignore the vertical component of the backsight and foresight, which are tied to the HI and HT measurements, and instead only use the vertical component of the common point observations. The final elevation of each traverse hub will still be defined using the measured HI, but the elevation of the trunnion axis of the setup, and therefore each measurement made from that trunnion axis, is being defined by the common point observations. And since these common points aren't changing vertically between traverse hubs, it's mathematically removing the influence of the height of instrument or height of target measurement from the network elevation. To field verify this common point or brace traversing methodology, I performed a 15 station traverse around a residential neighborhood that had a total length of 1,500 meters. All common points were ball prisms on either power poles, steel posts, or fire hydrants. Besides using common points, I did all my typical field calibrations prior to running control. Compensator calibration, ATR calibration, horizontal and vertical collimation calibration. I checked and adjusted my rod height. I checked my tape measure. I checked my optical plummet, so on and so forth. This method is going to help increase accuracy, but you still need to be on your game. After post-processing my data in StarNet as is, without removing the influence of HIs and HTs yet, the vertical closure to the common point and traverse hub that I separated to create an open traverse was 1.1 millimeter and 1.0 millimeter. Truth be told, I was hoping for a larger vertical discrepancy to highlight the effectiveness of this post-processing technique, but it is what it is. And even though I wasn't yet limiting the vertical component of the traverse to the common points, I was still using them. The adjustment was considering both the common points and the traverse hubs at this point. I then removed the common points from the adjustment to see what my vertical closure would have been had I never measured them in the first place, and the vertical closure on the traverse hub doubled to 2.4 millimeters. And finally, I brought my common points back in and post-processed the data to remove the vertical component between traverse hubs, and thus the influence of those HIs and HTs in the final vertical closure for this 1,500 meter traverse was 0.4 millimeters and 0.2 millimeters. Now I know I'm going to get some skepticism because we're dealing with such small errors here, so I'm leaving all of my raw data and my StarNet project file in the download link in the description of this video. I promise there's no funny business going on, and please feel free to go through the raw data and attempt to replicate my results. The thing is, from a mathematical standpoint, I could have measured the HI or HT wrong by 10 centimeters, and it would have zero influence on the vertical accuracy of the network, not each individual traverse hub. And to highlight this, I went back into my raw data and added in error to my HI and HT measure-ups. I randomly introduced between 2 to 3 millimeters of random error to the traverse hubs on about 60% of the setups. I felt between 2 to 3 millimeters was very plausible in situations where someone wasn't compensating for a slant height HI or was trying to measure HT to the side of a prism on a tripod. After introducing this error, I processed the traverse 3 more times. First, with common points removed and the vertical closure, it was 11 millimeters. Then, with the common points back into the adjustment, but not yet removing the influence of HIs and HTs, the vertical closure shrunk by about 50% to 6.9 millimeters and 6.8 millimeters. This is evidence that the random error in the HI and HT measure-up is compounding into both the final closure and all the points in the network leading up to that final closure. Finally, I processed the traverse with the HI and HT influence removed, and if I did everything correctly, my misclosure should have been identical to the adjustment I did with no error introduced, and that's exactly what I saw. Once again, I had a misclosure of 0.4 millimeters and 0.2 millimeters. One more time, we can't forget that your HIs, while not compounding error, are still affecting your traverse hub elevations, so be careful. Make sure you're compensating for a slant measurement, you're using a tape measure marked with millimeters, and check it to make sure it doesn't have an offset baked into the end. If you do all this, you can get some remarkably accurate results. Closing out to sub-millimeter over 15 stations in 1.5 kilometers is a little bit of luck, but it also probably wouldn't have happened without specific field and office procedures. From a mathematical standpoint, I don't know if there is a valid counterargument to be made on whether or not this method will be more accurate than a traditional traverse. If you just sit down and run through the error propagation, it's just going to be more accurate unless you employ it using some wacky techniques. It just comes down to comparing the vertical accuracy of a pair of measurements to a static point versus the accuracy of measuring your height of instrument and height of target. The question as to whether or not the extra effort is worth it, now that's 100% valid. And that's a question I can't answer for you. It depends on the accuracy needs of your project. When I floated this idea on the RPLS forum, several surveyors raised the question as to whether or not the additional time to set and tie your common points is more than running a traditional horizontal traverse and then going back and running a differential level loop on all of your hubs. Now, I can't speak for anyone else, but there's no question in my mind that there's no way that running a level loop on top of an existing traverse will be faster than setting and measuring a couple common points between each leg. Like previously mentioned, I use ball prisms and I can fit 2 setups inside of my 3D printed box I made. In that case, fits very easily in my vest pocket, and deploying a ball prism takes me maybe 15 seconds to set up and then another 15 seconds to take down and put away. If you're running full-size tripods and tribracks, then yeah, that's going to slow you down, but that's typically not how I traverse. I run with 2 ball prisms and 2 mini tripod setups in my vest and carry my pole and bipod when obstructions or refraction considerations don't allow for the use of mini tripods. I'm mobile and I'm fast with this setup. Now, running common points have other benefits too. Real-time blunder detection in the field because I'm triangulating every leg. And if a blunder sneaks by, I can recreate the traverse through those common points in post-processing. Not just vertically, but horizontally as well. I can run through this whole process solo, which I'm not able to do, differential leveling. And if I lose a bunch of traverse hubs that were on the ground 5 months from now and I need to come back and set up, oftentimes I can reestablish these common points as they're much less likely to be disturbed. My center punch on a fire hydrant isn't going anywhere, and I removed a common point on a power pole, then replaced it a day later to see what kind of centering error I was introducing. Honestly, I was not expecting to see great results, but in the end, it ended up being about 1 millimeter or so I started marking my leg bolt holes in case I needed them in the future. A power pole obviously isn't extremely stable long term, but in a pinch, maybe. I'm just not buying the argument that a 2D traverse plus a level run will be comparable from an effort standpoint to this method of traversing in most situations, but of course, there's always going to be exceptions. But when we start talking about working in areas with significant vertical relief, then the gap in time, effort, and quality between trig leveling and just differential leveling starts to shrink even more, but that's a topic for another video. I'd like to thank Jesse Kozlowski for both writing the paper that inspired this methodology and taking the time to sit down with me and let me pick his brain about trig leveling. Likewise of Austin Blaney that shared some of the insights he gathered over the years, setting ridiculously accurate dimensional control, and James Johnston of StarNet for letting me bounce ideas off him to get this method across the finish line. I've said it before and I'll say it again. Being fortunate enough to converse and learn from the legends of the surveying industry is by far the most rewarding part of making these videos. And for anyone that disagrees with any part of the method suggested here today, please do me a favor and don't keep it to yourself. Let me know what I got wrong in the comments, and if I agree, I'll be sure to pin that comment so we can all learn. And if I disagree, I'll let you know why, and hopefully we can have some productive discourse. I certainly don't know it all, and you could fill a warehouse with what I don't know, but this channel is all about the journey of learning, and that warehouse full of gaps in knowledge is a bit smaller than it was a few weeks ago, and with any luck and continued support from this amazing industry, it'll shrink again in a few weeks from now. And it's my hope I'm not the only one gaining something from these videos. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.